Two containers A and B containing the helium gas are prepared at room temperature with volume V and 1/3 of V, respectively. The pressure in A is 2P while the pressure in B is P. Find the pressure in A after the gas in B is added to it. Assumes the helium gas is an ideal gas and the temperature is unchanged. Since we assume the helium gas is an ideal gas, then the gas must obey the equations of state. PV equal to nRT, where the P is pressure, V is the volumes, N is number of mole, R is the gas constant, and the T is the temperature in Kelvin. Now we can write down the equations of state for the gas in container A, which is 2PV equal to nART, because the pressure in the container A for the gas is 2P. This is 2P and the volume is V, and the number of mole we denote it as Na, and the temperature T is we denote it as a capital T. Similarly, the container B, the gas in the container P, it obeys the equation of state, and we can write down as the P, pressure of the gas in container B, times the volumes of the gas in container B, which is 1/3 of the V, and the number of mole of the gas in container B is Nb, and the temperature T is the same as in the container A. So that's why in these two equations, the T and T is the same. Now the R, of course, is the same because it is just a gas constant. So we have the equations 2 now for the gas in container B. If now the gas in the container B is added to the container A, then the new pressure of the container A, we denote it as a P prime. This is the things that we want to find, which is a P prime, and the volumes of the container B A is a V, same as the V in the equation number 1, and the number of mole of the gas now in the A after the gas in the B is added becomes Na plus Nb. And since the temperature is unchanged, so we have the same symbols T for the temperature. Now, since we want to find the P prime, therefore we change this P prime as a subject by moving the V to the right hand side of the equality sign. So we have these expressions. We substitute the Na and the Nb by using the equations number 1 and number 2. We obtain this for Na, it is 2PV/RT, and then for Nb it is PV/3RT. So we have this Na and the Nb in terms of the PV and T. So now we can cancel the RT, and this RT cancel, and the V also can be cancelled. Therefore, it remains the first term. In the first term, 2P, and in the second terms, it is P/3. So if we add up, we will get the new pressure P prime in the container A after the gas in the B is added is equal to 703 P. Now, initially, the container A has the pressure 2P. Now it becomes 703 P. So that means it is more than 2P. So that means the pressure in the container A becomes bigger after the gas in the B is added to the A. The pressure increase. From the equations of state PV equal to nRT, we can note that the reasons the pressure in the container A is increased to 703 P. It is because of the number of mole or number of molecules in the container A now is increased. Based on this equation PV equal to nRT, we know that the T is constant, unchanged, R is a constant. V also for the container A, it is not changing. Before the B is added to A and after the B is added to A, the container of the A, its volume is not changing. So that means due to the change of this N in the container A, change from Na to Na plus Nb, so that means it's increased. The pressure P also will increase. So from this example, what we can see is that if the number of the molecule in the container is increased, then the pressure also will be increased. If the temperature T and the volume is a constant. So that means P is directly proportional to the number of molecule in the gas, number of mole in the gas, or also number of molecule in the gas.